All right, so today we are going to be going over combinations of functions, which is just taking two or more functions and performing operations. So we're going to be adding, subtracting, multiplying, and dividing. And as you can see here, these are our rules, and this is in function notation. So here, looking at this first sum, how you would read this is we're adding f and g, and this second set of parentheses is not multiplied by x. What this means is this is our input. This is what we are inputting into f and g. So technically how you would read this is f of x plus g of x. And the same rule goes for subtraction, multiplication, and division. The two letters here are our functions, and the second set of parentheses defines our input. So on the second one, we are subtracting f of x minus g of x. Now, order matters. It doesn't really matter for sum or product, but order matters for difference and quotient. This makes sense, or it should make sense, because 2 minus 4 is different than, as we're about to write the same thing again. Ooh, my Surface is not liking me right now. It's not even erasing. Erase! Okay, cross that out. It's not erasing. 4 minus 2. So these are two different outputs. Negative 2 and 2 are different. The order of the functions matters here. Okay, so then product is just f of x times g of x, and quotient f of x divided by g of x. Now, we'll talk about this a little bit more in a second, but the domain of the combinations is where the two original domains for f and g overlap. So it's the domain that they share. And like I said, we'll go over it in a second. All right, so let's apply it. We're asked to do these 4 different combinations. First, we're asked to do f of x plus g of x. Remember, this second set of parentheses, what is our input? Which, lucky enough for us, for these problems, x is already the input on f of x and g of x. I don't need to substitute in anything different. It's already input for us. So what we do is we take all that f of x is equivalent to, x squared, and we add it to all that g of x is, square root of x plus 1. And then we simplify. Can this product or this sum be simplified any? It's not a trick question.
Can't you get rid of the squared and the square, like the square root?
I can't. The only thing that gets rid of square roots is if I were to square just this, which I can't do because that would technically be changing the size, the value of our answer. So when I'm just adding like this, these are unlike terms. One's an x squared, one's a square root. They're unlike terms. They can't be combined. So this is our answer. Then, moving on, now instead of adding, we're just subtracting. But again, these are unlike terms, so my answer remains. I cannot combine these at all. This can't be simplified. I'm done. Next, I'm multiplying, so I'm taking all that f of x is and multiplying it times all that g of x is. I gotta figure out why it's so delayed. I can't imagine being a student. I'd be so annoyed. All right. And then lastly, we take all that g of x is and divide it by, I'm sorry, all the f of x is, because f is on top. So all that f of x is divided by all that g of x is. Now technically, we should simplify this some more, but we're not going to because we don't want to get into all that. But technically, we should simplify this because we're not allowed to leave a square root in the denominator. But we won't ask you to do that, so I'm not going to go over it right now. Wow. Okay, there we go. Took forever to erase. It's like illegal math. In geometry, Lauren, I would never let you leave that. We would have to, it's called rationalizing the denominator. We would have to get rid of that square root in the denominator by doing this. Right? So then that would be 2 times square root of 3 over 3. So technically here we would have to, but we're not going to do it. But this is what we would do. So technically that's the true answer. But like I said, we don't really need to be worrying about that right now. I'm not going to do it. All right. So now we have to go over the domains. We have to go over the domains of each one of these combinations. Now, like I was saying before, the domain of a combination is where the original domains for the original functions overlap. So we need to figure out what is our domain, what was our original domain for f of x. There we go. Thank you, Kate. Thank you, Aubrey. My gosh. The domain of x squared is all real numbers, right? That is a quadratic. So our domain is all real numbers. I'm going to say negative infinity to infinity. And then, what is our domain for g of x? This one's a little bit more tricky to think about. What I'm going to show you on this graph is what the parent function of an x squared or a square root of x looks like. This is the parent function. How does g of x differ from the parent function?
Would it be, this is might be wrong, would it be negative 1 comma infinity?
Exactly. Yes, because it was moved left 1, right? So this function has been moved left 1. That's what the plus 1 does. So now our domain is from negative 1 to infinity. So now knowing those two domains, what is our overlapping domain? What domain do they share? Right, they go, the max value is positive infinity. What is the minimum value that they both share? Yes. So our overlapping domain for each one of these is from negative 1 to infinity. The last one, however, does change. It's a little bit different. Now, just based on how long it's taking people to answer today, I'm going to assume that you don't know the answer here for what the domain would be. So I'm just going to write it. But does anyone know why? Why did it change?
Is it because it's a fraction?
Yes, okay. It is because it's a fraction. But why? Think about this. going from this domain where we're including 1, we're now not including negative 1. What is it about negative 1 that we cannot have in this fraction? Why can we not include negative 1? Try doing it. Try inputting negative 1. What happens? We're aha! Right there. Over 0. What happens in your calculator if you put divide by 0? Error. It's undefined. You can never divide by 0. So here in this domain, we cannot include negative 1 because if we did, this would be undefined. We cannot divide by 0. I'm going to have to take this recording and cut out all the long pauses. Okay. Moving on to page number 2. Any questions? Hopefully not. We're going to assume there's not. And move on. All right. So now the difference here on these examples is instead of inputting x, we're now inputting 3. So we have another step that we have to do. Now notice that 3 is the input on all 4 of these. And before we're doing the combining, we should be inputting 3 first. So my suggestion is, because we're inputting 3 every time, you should first figure out what the input of 3 gives you for both functions. So up here, I'm going to input 3, which means instead of an x, I'm going to write 3. 3 squared is 9, minus 5 is 4. And then I'm also going to input 3 on g of x, which again means that wherever I see an x, instead I'm going to write 3. So this is the absolute value of 3 minus 7. 3 minus 7 is negative 4, but it's the absolute value of negative 4, making it a positive 4, plus 2 is 6. So now it's very, very straightforward. Now that we've already found our inputs of 3 and got the output of 4 for f of 3 and 6 for g of 3, all we now have to do is combine. So first we have f of 3 plus g of 3. That is 4 plus 6, which is 10. Boom, done. Then it's not times, I see. Yeah, remember, this is not, this notation, the 3 after the f plus g is not multiplied by 3. This 3 defines our input. So how this reads is f of 3 plus g of 3. It's not multiply by 3. It's just 10. It's just 10. The answer is just 10. So now we're going to do g of 3 minus f of 3. So that's 6 minus 4, which is 2. And that one's done again. It's not multiplied by 3. It's just 2. This is why earlier I said order matters for this problem exactly. If instead it had f minus g of 3, it would have been 4 minus 6, which is negative 2. So those differ. You have to make sure you're doing the correct order, the order it's talking about. Then we're going to multiply g of 3 times f of 3. So that's what was g of 3? 6 times 4.
Wait, miss, why did you switch
Switch what?
the F and G?
I wanted to show you why order mattered, because if we did switch them, it'd be a different answer. So it's like an example I did right there.
Oh, gotcha.
Ah, yeah, maybe you should like box that in and make sure that you know that that's a different problem. So 6 times 4 is 24. Then we're doing f of 3 divided by g of 3. So that's, what was f? F was 4, right? Divided by g of 3, which is 6. And then we just simplify that. 4 divided by 6 simplifies to 2/3. Any questions when we're inputting a different value other than x? All right, so now our last thing that we're going to go over is graph combinations, which is still the exact same concept as above, just instead of figuring out which each combination is when we're only inputting one x value, now we'll be inputting a whole bunch of x values. But this is really super easy when looking at a graph, because you're just finding those x values on the graph and figuring out what your function's y value is at that point. So for both f and g, first I'll look at my f of x. So again, this x column here is my inputs. I'm finding those x values on the graph and figuring out what y value the function has. Uh-oh. My OneNote just crashed. All right. No. So on our graph, you find I have what f of x value at that point. We're looking at this graph first, right? This f of x graph. So when our x value is -5, what is the y value for that point?
3.
Yes, 3, right? On our graph, we just find -5 and we follow -5 upward until we hit our line, our point. And that point has a y value of 3. 2. -2 on the x-axis. If I follow that -2 upward, what's my y value at that point? This one you kind of got to guess at. I hate guessing, but that's what you got to do.
2.
Yeah, I would say 2. When your x value is 0, what's your f of x? -2, yes. When your x value is 2, what do you have on f of x? 1. When your x value is 4, what's f of x? 1. Oh, wait, whoa. No. It's 4. And when your x value is 5, your f of x is 0. Good. Now we repeat, but for g of x. So we're using the exact same x values, but now we're looking at the second graph there. When x is -5, what is our g of x value? 0. When x is -2, what's our g of x? Yes, -3, good. When x is 0, what is g of x? Yes, -1. When x is 2, what's g of x? -3, is that right? Yeah. When x is 4, g of x is 1. And when x is 5, g of x is
3.
all right. So now on our table, when we're combining f of x plus g of x, we are only looking at the outputs that we got. So we're going to be adding what we got for f of x plus what we got for g of x. So our first one is just 3 plus 0, or 3. Then 2 plus negative 3 is negative 1. Negative 2 plus negative 1 is negative 3. 1 plus negative 3 is negative 2. 4 plus 1 is 5, and 0 plus 3 is 3. And then we are going to be asked to graph the combination. So we still are using the exact same we've been using this entire time. Oh, not input. I didn't mean to say that. I mean, I did mean to say that. I didn't mean to write that. We're using the same input of x. That's what we're graphing as our x values. But our y values are the combination that we just found. So on this first line, if we're graphing the combination, we're graphing the point negative 5, 3. And then the next line, we're graphing the point negative 2, negative 1. And then 0, negative 3. And then 2, negative 2, 4, 5, and 5, 3. Well, what happens is you look at your first graph and you're looking for the perfect points, and all you have to do is write down those x values. So this perfect point here is an x value of negative 5. This point has an x value of negative 1. This point has an x value of 0. And this point has an x value of 5. And then you don't need those last two. So then you just write down for those points the y values on t, the t of x values. So for that first point, it's 1. The second point is 2. The third point, it is, what is that, 4? And for the fourth point, that y value is 0. And then you repeat. So we're finding the r of x values now with the same inputs. So I'm looking when x is negative 5, my y value, my r of x value is negative 1. When x is negative 1, again, my r of x value is still negative 1. It's this point right here. When your x value is 0, your r of x value is, what is that, negative 4? And this last point here, when my x value is 5, my r of x value is negative 3.
Okay, thanks.
You're welcome. And then you just, I can quickly just show you, if you want, the subtraction. You just have to remember it's 1 minus negative 1, which is actually a 2. Because minus negative 1 makes that a plus 1. Same thing here. 2 minus negative 1, that makes it a 3. 4 minus negative 4 is an 8. 0 minus negative 3 is a 3. And then when you're going to graph these, you're graphing the x values, the initial inputs, and the combination outputs, t minus r. So that's negative 5, 2, negative 1, 3, 0, 8 is way off our graph, and 5, 3. And then you connect and you're done. This is the combination t of x minus r of x.